This is the sixth video in a series devoted to differential equations. In the previous video, we looked at exact differential equations, as well as the solution strategy for such differential equations. And now we're going to look at the proposed ability to translate a non-exact differential equation into an exact differential equation. And this is a really important theme in differential equations, and that is to take a differential equation that we do not have the techniques to solve and somehow translate it into a differential equation that we do have the techniques to solve. So we saw this in previous videos for other types of differential equations, and now we're going to look at it for non-exact to exact differential equations. Okay, so let's recall a definition first. So we say the differential equation p of xy plus q of xy, y prime equals 0 is exact if the partial of q with respect to x is equal to the partial of p with respect to y. So just for space, I'm using this subscript notation to mean the partial derivative. And then if it's exact, we have a solution guaranteed to be implicitly described by this equation f of xy equals a constant, where the partial of f with respect to x is p and the partial of f with respect to y is q. And this type of function is guaranteed to exist because of a result in multivariable calculus, which we discussed in the previous video, having to do with the curl of a vector field being 0 and that implying the existence of a so-called potential function, which we won't go over here. And so, like I alluded to, today we're going to talk about the ability to translate a non-exact differential equation into an exact differential equation. And we'll explore this possibility by multiplying our given differential equation by a function. Okay, so let's maybe write the question down carefully. So given a non-exact differential equation, p plus q y prime, can we find a function mu, which is a function of x and y, such that mu times p plus mu times q times y prime equals 0 is an exact differential equation? Okay, so let's explore what it would take for this to be exact, and then we'll look at some special cases. So for this to be exact, we need the partial with respect to y of mu times p to be equal to the partial with respect to x of mu times q. So that's just translating this condition over here to this new differential equation, which has been multiplied by mu. Now we can expand each of these using the product rule. So this is going to give us mu sub y times p plus mu times p sub y, where by those subscripts I mean partial derivatives. And then this equals mu sub x times q plus mu times q sub x. So we need that equality to be true. But now we can move some things around, and we can write this as mu sub y times p minus mu sub x times q equals mu times q sub x minus p sub y. So that's pretty much all we can do for simplification, because the only thing that resemble like terms are this guy and this guy, as they include just a function mu. Okay, another thing that I'd like to notice is that if mu equals a constant, so if mu is just a constant function, then this entire left-hand side is 0 because both of these partial derivatives are 0. But that means this right-hand side is also 0. But if this right-hand side is 0, well then either mu is 0, which is not super interesting, or q sub x minus p sub y is 0, which gives us this condition right here. Okay, so that's pretty interesting. Now I'd like to maybe make an important comment, and that is, in general, finding this mu is hard or difficult. So let's write that down here. So generally, finding such a function mu, this integrating factor, is difficult or impossible. Like it may not exist. And if it does exist, well, generally, it's going to be hard to come up with it. That's why we'll look at some very special cases. And the first special case will be if mu is a function of x times a function of y, and we'll start exploring that on the next board. So during our explorations for mu times p plus mu times q times y prime equals 0 to be an exact differential equation, we've determined that that is equivalent to the following equation. So the partial with respect to y of mu times p minus the partial with respect to x of mu times q equals mu times q sub x minus p sub y. And now we noted on the last board that finding a general mu is either impossible or very difficult. So we're going to look at some special cases. And I don't know if you've noticed, but there are a lot of times in these videos where I say, well, solving this type of differential equation in general is very difficult or impossible. So we're going to look at some special cases. And that is generally true for the subject of differential equations. So it's very easy to write down a differential equation that has no analytic solution or no solution involving elementary functions. And so because of that, we just explore special cases. And that might seem like a cop-out, but often you can approximate these impossible to solve equations by possible to solve equations. Okay, so anyway, here we're looking at the question, what if mu of xy equals a function of x times a function of y? So we looked at functions of x times functions of y when we had a separable differential equation. So just keep that in mind. Okay, so if we have this, then mu sub x is equal to f prime of x times g of y. I think I said g of y, but I had g of x written. So that's g of y. Maybe Justin will point out that I've got a typo there on the board. And that's because the product rule doesn't apply here because this function with respect to y is a constant with respect to x. And then for similar reasons, we have mu sub y, the partial with respect to y, is f of x times g prime of y. Okay, so now we can plug that into this equation, and let's see what that gives us. We'll have f of x times g prime of y times p minus f prime of x times g of y times q equals mu, which is f of x times g of y times q sub x minus p sub y. So something like that. And then notice that if we divide by f of x times g of y, in other words, if we divide by mu, this will simplify a bit. This whole thing over here will disappear, and then we'll have partial cancellation on the left-hand side. Okay, so just to reiterate what we're doing, we're taking this entire equation and we're multiplying by 1 over mu, keeping in mind that mu is equal to f of x times g of y. So that's going to give me g prime of y over g of y times my function p minus f prime of x over f of x times my function q equals my partial q of x minus p of y. Now this is interesting because this looks like a logarithmic derivative of the function g. This looks like a logarithmic derivative of the function f, which we've seen in previous types of problems. And now this was good exploration, but unfortunately we're going to have to simplify this even more to get at something which is immediately workable. And that is, well, what if mu is really a function of x? So instead of being a function of xy, it's just a function of x. So in the language up here, we would have f of x equals the entire function mu, and then g of y is just the constant function 1. So if g of y is the constant function 1, its derivative is 0. So let's see. This fact right here means its derivative is 0, which means this would cancel. And then we would have mu prime over mu. So let's see, this gives us mu prime over mu equals p sub y minus q sub x over q. After we've taken this minus sign and had it flip the order of subtraction, and then maybe divided by q. Okay, so this is actually quite a bit more helpful than it might look because this left-hand side is only a function of x. And we know that it's only a function of x because we're looking at this super special case right now where our integrating factor mu is only a function of x. So just to reiterate, we took this simplification step right here based off the fact that the general case looked too hard. Then we got down to this. We said, well, this case also looks pretty hard. So let's make another simplifying step just so that we can at least come up with a solution. And we finally came up with something that's workable. So if mu is a function of x, then mu prime is a function of x, which means their quotient is a function of x. But if the left-hand side is a function of x, then the right-hand side is also a function of x. So what does that mean? So that means our non-exact differential equation is transferable to an exact differential equation using multiplication by a function of x if and only if this red boxed thing, which I'm starring in blue, is exactly just a function of x. So in other words, when you calculate this guy right here, all dependence on y disappears. Okay, so we know when such a integrating factor exists, but check it out. We've set up a differential equation for this integrating factor. And we can solve this using methods on a previous video, just taking the antiderivative of both sides. This is a logarithmic derivative, so this is going to give us like the logarithm of mu. And this will just be the symbolic antiderivative of this. But that means we'll have to exponentiate to get mu. And what we'll see is mu of x is equal to exp of the antiderivative of p sub y minus q sub x over q dx, whereby x I mean e to all of that. Okay, so putting it all together one more time, a non-exact differential equation, p plus q y prime equals 0, is translatable into an exact equation by multiplying by mu, where mu is just a function of x, exactly when p sub y minus q sub x over q is only a function of x, in which case mu is equal to e to the power antiderivative of p sub y minus q sub x over q dx. And you might imagine that there's another version of this where mu is just a function of y. And in fact, there's even another version of this where mu is like a nice combination of x and y. And we'll summarize those on the next board before looking at some examples. So now for a summary of what we just saw. So the differential equation p plus q times y prime equals 0 can be transformed into an exact differential equation by multiplying by mu. So in other words, mu times p plus mu times q y prime equals 0 is exact, where mu is only a function of x, and that function of x is described by the exponential of the antiderivative of py minus qx over q, if and only if this integrand is only a function of x. So that's what we explored on the last board. Now, similarly to what we explored on the last board, we've got another result where mu is just a function of y, in which case it's the exponential of qx minus py over p, if and only if that integrand is only a function of y. So that's essentially just in parallel to what we saw before. We've got this one more, which is a little bit more technical, which says that mu is a function of x times y, if and only if mu x minus py over xp minus yq is a function of x times y. And in that case, it's the exponential of the antiderivative of qx minus py over xp minus yq, where we've replaced all the x times y with t, and then we integrate it up to xy. So like I said, that's a little bit more technical, but what's going on here is that this integrand is a function of one variable. That one variable just happens to be the product of x times y. So there will be x's and y's in this object. It's just all of those x's and y's are wrapped up into x times y. So there's no free x, there's no free y, if you will. Okay, so let's do a little bit of a proof of number 3. So let's say if mu is a function of xy, then we can calculate its partials. So notice the partial with respect to x of mu is equal to, by the chain rule, it'll be mu prime of xy times the partial with respect to x of xy. So this is going to be y times mu prime, because the partial with respect to x of xy is y, as y is a coefficient of x. So maybe a nice way to think about this is we have mu depends on a single variable, which is called xy, and this variable xy depends on xy. So we've got this variable dependence tree, if you will. And then furthermore, we can calculate the partial with respect to y of mu. So that'll be the derivative of mu with respect to x times y. So that's going to be mu prime of x times y. And then the partial with respect to y of x times y. So that's going to give us x times mu prime. Okay, and then we know that mu p plus mu q y prime equals 0 is exact if and only if the following holds. So that will be the partial with respect to x of mu q equals the partial with respect to y of mu times p. So that's just the straight condition for this thing to be exact. Okay, but using this calculation that we have up here, where we've got this partial with respect to x is y times mu prime, this partial with respect to y is x times mu prime, along with the product rule for each of those give us the following new equation. So we've got y mu prime times q plus mu q sub x. So that's what we get from taking the partial with respect to x of the left-hand side. And then we'll have that's equal to x mu prime p plus mu p sub x. That's the partial with respect to y of mu times p. So putting this all together and moving things around, we'll see that mu prime over mu is equal to q sub x minus p sub y over x times p minus y times q. That's just rearranging this equation. But notice that this left-hand side is a function of xy. X times y seen as its own variable. So that means we can take the antiderivative of both sides with respect to xy. So doing that, maybe we would rewrite this as the antiderivative of mu prime over mu of t from something up to xy dt. So that's maybe the careful way of writing the antiderivative with respect to xy, keeping in mind that what we mean by a function of xy is really a function of one variable where that variable is xy. So that's the antiderivative of the left-hand side. The antiderivative of the right-hand side is the same kind of thing. So the integral from something up to x times y, q sub x minus p sub y over xp minus y q dt, where we're thinking of this as a function of t, a function of a single variable. But taking this antiderivative gives us some sort of natural log of mu. Taking this antiderivative, well, that's just symbolic. And then exponentiating gives us this result over here. Okay, so that's good for this third one. Now let's look at some examples. So for our first example, we'll look at 5xy plus 2x plus 5 dx plus 2x dy equals 0. So let's recall that this is written in so-called differential form, which is slightly different than from what we have over here and what we've been writing down all day. But we did look at this in a previous video, and this is a standard way to write exact differential equations as well, or differential equations in this exactness setting. Okay, so you can actually check this as non-exact, which means, well, since we've only worked out these cases, we want to calculate these types of objects. and see if they're functions of x, functions of y, or functions of xy to set up our integrating factor. So let's start maybe by looking at this one. So let's look at p sub y minus q sub x over q and see what we get. Keeping in mind that with this setup, this function is equal to p, and this function 2x is equal to q. Okay, so taking the partial of p with respect to y will give us 5x minus 2, that's the partial of q with respect to x, all over q, which is 2x. So in the end, this gives us 5x minus 1 over x. Okay, but notice that's exactly just a function of x. So this is a function only of x. But since that's a function of only x, that means an integrating factor, which is a function of x, will in fact exist, and it will be equal to this object, the exponential of the antiderivative of this thing that we've already calculated. Okay, so let's now set mu of x equal to the exponential of the antiderivative of this thing right here. So luckily, in order to check if such an integrating factor exists, we've already done some of the work. Now we just have to take the antiderivative of this and exponentiate it. Okay, so we've got 5 halves minus 1 over x dx. So this gives us the exponential of 5 halves x, and then minus the natural log of x. So minus ln of x. So something like that. But we can take this minus sign, change it to a plus sign by writing that as the natural log of 1 over x. And then we can take this sum in the exponential and turn it into a product outside. That'll be e to the natural log of 1 over x times e to the 5x over 2. Natural log of 1 over x is just 1 over x. Those cancel. So we've got 1 over x times e to the 5x over 2. So we have something like that. But that's our function mu, and by this stuff that we've checked over here, that we've built over here, it's guaranteed that if we multiply our original differential equation by mu, it will be an exact differential equation. So let's start the next board with that new differential equation. Starting with this differential equation, we calculated an integrating factor which transforms it into an exact differential equation. By our results over here, we knew the integrating factor was just a function of x. We calculated that to be 1 over x times e to the 5x over 2. Now I've taken our starting differential equation and multiplied by that integrating factor. And now this thing is guaranteed to be exact by like our setup. So you can check that this is exact, but we won't do that because again, like I said, it's guaranteed by our setup. So what do we need? So we need to find a function f of xy such that the partial with respect to x is this function which is attacking the differential dx. So in other words, we've got 5y e to the 5x over 2 plus 2 e to the 5x over 2 plus 5 over x e to the 5x over 2. And then we need the partial with respect to y to be this coefficient of the dy differential. So that's going to be 2 e to the 5x over 2. And now we'll use the strategy that we built in the last video in order to calculate f given these partial derivatives. So let's start with f sub y because it's a little simpler. We have this is 2 e to the 5x over 2. And now we'll start by taking the antiderivative of this with respect to y. So taking the antiderivative of this with respect to y, we'll get f is equal to 2y e to the 5xy. That's because all of this is a constant with respect to y. So the antiderivative of a constant is just a constant multiple of y. And then we'll have plus a constant with respect to y. But a constant with respect to y is just a pure function of x. I'll call that g of x. Okay, nice. And now from here, we'll take the derivative with respect to x and compare it to this version of f sub x, which we know to be true right here. So taking the derivative of this with respect to x will give us 5y e to the 5x over 2. So let's maybe point out that here we're taking the derivative with respect to x plus g prime of x. Great. And that needs to be equal to this f sub x, which maybe I'll just like make a little diagram. It must be equal to this thing right here. Okay. So we can cancel some things out. Notice that this 5y e to the 5x over 2 will cancel this 5y e to the 5x over 2. And that's going to leave us with g prime equals whatever's left over. So let's copy that down here. So g prime of x equals 2 e to the 5x over 2 plus 5 over x e to the 5x over 2. That means our function g is the antiderivative of this. So taking the antiderivative of 2 times e to the 5x over 2 will give us 4 over 5 e to the 5x over 2, using a simple like chain rule or u substitution in there. And then we've got this function right here, but that has no elementary antiderivative. So we'll write that down just with its symbolic antiderivative. That might seem a little bit like a cheat, but that's as good as we can do here. That's actually called the exponential integral function, if you want to look that up. I think that's kind of interesting. In fact, on the main channel, I've got a video about that if you're interested. Okay, so this is plus 5, and then the antiderivative of e to the 5x over 2 over x dx. And that's a function all on its own. Okay, so let's see where we are. We've got f, which is a function of xy, is this 2y e to the 5xy plus g, where we've just calculated g to be all of that. And then in the end, we know that f of xy equals a constant will be an implicit description of our solution. But since y is only wrapped up into this function one place, right here, we can actually solve explicitly for y. And let's finish this example off by doing that. So we're working through a fairly sizable example, and we got down to an implicit description of our solution by this equation. Recall this entire left-hand side was what we calculated to be capital F, which was the potential function for the vector field defined by this comma this. Just sort of to put it into words that you might have learned in multivariable calculus class. But check it out. These two terms only depend on x. This has just one appearance of y, so we can easily solve for y. So if we easily solve for y, we see that y is equal to, let's see, a constant times e to the minus 5x over 2, and then minus 2 over 5, and then minus 5 over 2 times e to the minus 5x over 2, and then the antiderivative of e to the 5x over 2 over x dx. So I just skipped a couple of steps while doing that, but I think we can like telegraph through what's happening. So notice that if we divide both sides by 2 and absorb that division by 2 into our constant, this 4 will turn to a 2, and here we'll have a 5 over 2. And then we'll multiply by e to the minus 5x over 2. That will attach this e to the minus 5x over 2 to this constant. It'll cancel out this e to the 5x over 2, and then it'll multiply this antiderivative by that same term. And then solving for y, well, it gives us this thing right here. So I mean, this is a fairly advanced class that we're going through here. So this step, which is this yellow arrow, should be a fairly reasonable step for everyone. Okay, so let's do another example. Here's our next example. We've got 3xy plus 6y squared plus 2x squared plus 9xy times y prime equals 0. Again, we can check that this is non-exact. We won't do that here. And since we've only got these 3 ways of translating this into an exact differential equation at this moment, we'll hope that one of these will work. So that means we need to calculate this object right here, and this object right here, and see if this one is a function of x, this one is a function of y, and or this one is a function of xy, and then choose the one that is true in order to build our integrating factor. Okay, so I'll just tell you that this first one won't work. We'll just check the second two. So let's check q sub x minus p sub y over p to see if that is a function of y. So if this second case works. So let's just recall this function that is multiplying y prime is our function q. This kind of free function is p. Notice I've changed back to my other notation. I'm changing from one notation to the other just so that we remain familiar with both. Okay, so the partial with respect to x of q is equal to 4x plus 9y. Good. Then we subtract the partial of y with respect to p. So that's going to be 3x plus 12y. Then we divide all of that by p. That's 3xy plus 6y squared. Okay, so let's see. That's going to give us negative x. Then we've got 9y minus 12y. That's minus 3y all over. Well, we can factor a y out of this, and we'll have 3x plus 2y. But notice that's most definitely not a function of y. So let's point that out. So not a function of y. I guess I should say only of y. It also has x's in there that cannot be removed. Notice that we're sort of close to being able to remove them, as this numerator and this denominator have the same sort of shape, but they most definitely don't cancel in this case. Okay, so that means this second choice is out. I already said this first choice was out, but maybe you should check it on your own. Now let's look at this third choice. So we'll look at q sub x minus p sub y all over xp minus yq. So we already calculated qx minus py, that's minus x minus 3y in our first bit. Now we'll just calculate x times p minus y times q. So that'll be 3x squared y plus 6xy squared. So that's x times p minus, let's see, 2x squared y plus 9xy squared. So that minus sign factors through or multiplies through, so that's what we have. So just to reiterate, this is x times p, y times q. So let's see what will simplify. We most definitely have like terms. So this is going to be minus x minus 3y all over. So here we've got 3x squared y minus 2x squared y. That's going to give us negative x squared y. Then we've got this 6x squared y minus 9x squared y. That's going to be minus 3xy squared, I should say. Xy squared for each of those. Now we can factor an xy out of the denominator. That leaves us with minus x minus 3y. Got an xy factored out of the denominator. And then after factoring an xy out of the denominator, we have minus x minus 3y. Notice each of those cancel, so that's cool. And we have 1 over xy. So this is good news because this is a function of our single variable x times y. So it's got x's and y's in there, but they're wrapped up into this product. So that means that this third trick is available. So let's use this third trick to translate this into an exact differential equation and then solve. So given this differential equation, we calculated this quotient, which is part of our test for number 3, and we saw that this quotient was equal to 1 over x times y, which means this integrating factor described by number 3 is available to us. Okay, so now let's calculate that integrating factor. So that means we have mu is equal to the exponential of the antiderivative from a starting point up to x times y of 1 over t dt. Why do I have 1 over t here when here I have 1 over xy? And that's because we think about this thing right here as a function of one variable. So what variable should we use here? Maybe let's use alpha. So this is like alpha of xy, where alpha of t is equal to 1 over t. It's just, in this case, the one variable it depends on is x times y. So I don't know the best way to think about this, but I think this is a kind of reasonable way to think about it. Okay, well, notice that taking the antiderivative here will give us the natural log of t. We evaluate at x times y, and we'll get the natural log of x times y. So we have the exponential of the natural log of x times y. We might as well make this lower bound equal to 1 because the natural log of 1 is 0. But then the exponential and the natural log cancel, which gives us just x times y. And then all of this development ensures that multiplying by this function of mu will transform our starting differential equation into an exact differential equation. So let's multiply by this value of mu, x times y. So that gives us 3x squared y squared plus 6xy cubed, and then plus 2x cubed y plus 9x squared y prime equals 0 is exact. Really, it must be exact by this construction that we have here. Okay, so that means we need to find a function f so that f sub x is equal to our new p function, so this function which I've underlined in pink, and the partial with respect to y is this q function which I've underlined in pink as well. Okay, so we need the partial with respect to x of f to be 3x squared y squared plus 3xy cubed, but taking the antiderivative with respect to x, that gives us our function f is equal to, let's see, that's going to be x cubed y squared plus 3x squared y cubed plus a function of y. We got that function of y because we're taking the antiderivative with respect to x, so any constant is really a function of y. Now we'll take the we'll take the derivative of this with respect to y, so the partial derivative of this with respect to y, and it has to be equal to that thing which is just above. Okay, so the partial with respect to y will leave us with 2x cubed y for this first term, and then we'll have plus 9x squared y squared for this second term, plus g prime of y for this third term. So that must be equal to this thing right here. But this 2x cubed y already exists. This 9x squared y squared already exists. So we have just g prime of y equals 0 after everything cancels, which means g is a constant. But since we get a constant at the end from setting our f equal to a constant, that means that we might as well just take this g to be the constant equal to 0. So what that means in the end is that our solution is implicitly described by f of xy equals a constant. In other words, x cubed y squared plus 3x squared y cubed equals some constant c. And that would be our implicit description of our solution to our starting differential equation here. Okay, let's look at maybe one more example. So for our last example, we'll look at the non-exact differential equation y dx plus x squared y minus x dy equals 0. And I say it's non-exact, but we won't check that. Another thing that I will not check is that this doesn't satisfy any of these kind of canned tricks that we have. So that being said, we need a new trick, and this will be the last trick that we have here, which is like, in some ways, a simultaneous generalization of all of these. And this new trick is maybe based on the question, maybe mu equals x to the a, y to the b, where a and b are too determined will work. Okay, so what does that mean? So that means we'll take the differential equation that we're starting with and we'll multiply by mu in this form, impose exactness, and then use that imposition of the exactness equation to solve for a and b. Okay, so multiplying by mu will give us x to the a, y to the b plus 1 dx, plus x to the a plus 2, y to the b plus 1, minus x to the a plus 1, y to the b, dy equals 0. Okay, good. And now in the language of what we had before, this function right here is our function p. This function, which is a coefficient of dy, is our function of q. So what we need for this thing to be exact is we need the partial with respect to x of q to be equal to the partial with respect to y of p. So let's see what that gives us. The partial with respect to x of q using the power rule will be a plus 2 times x to the a plus 1, y to the b plus 1, minus a plus 1 times x to the a, y to the b. So that's the partial of q with respect to x, like I said, using the power rule. And then the partial of p with respect to y will give us b plus 1 times x to the a, y to the b. Great. But now let's notice a couple of things. We've got an x to the a, y to the b term on both sides of the equation. The fact that there's one of those on both sides of the equation means their coefficients must be equal. In other words, we need minus a plus 1 to be equal to b plus 1. But if minus a plus 1 equals b plus 1, that means that a equals minus b, or b equals minus a, depending on which one's most appropriate. Now let's also notice over here on the left-hand side of the equation, we have an x to the a plus 1, y to the b plus 1 term. And on the right-hand side, there is no such term. That means this coefficient, a plus 2, must be equal to 0. But if a plus 2 is equal to 0, that means a equals negative 2, which means b equals 2. But that means our mu must be equal to y squared over x squared. Again, using this form for mu. So let's finish this problem off using that integrating factor. So in the last board, we had a differential equation which we determined could be translated into an exact differential equation by multiplication by a mu, which was y squared over x squared. I was missing a 1/3 here, but that doesn't change any of the calculations that we did on the previous board. Okay, so now let's multiply by this value of mu and see what we get. So that's going to give us 1/3, and then we'll have y cubed over x squared for this dx, plus, let's see, we will have y cubed here minus y squared over x dy equals 0. Okay, so that's good. So using our standard solution strategy for solving exact differential equations, we need a function f of xy such that the partial with respect to x is this function, so 1/3 x cubed over y squared, and the partial with respect to y is this function. So that's going to be y cubed minus y squared over x. Okay. Let's maybe start with this and go down that path. So if the partial with respect to y is y cubed minus y squared over x, then taking the antiderivative with respect to y will give us a form of the function of f of xy equals 1/4 y to the 4th minus 1/3 y cubed over x. Great. Now let's take the partial of this, and then plus a constant, but that constant will be a whole function of x, given the fact that we took an antiderivative with respect to y. Great. Now let's take the partial of this with respect to x and match it with what we know the partial with respect to x should be. So taking the partial of this with respect to x will give us 0 because it only has y's in it. Partial of this with respect to x will turn the x in the denominator to an x squared and cancel this minus sign out, leaving us with 1/3 and then y cubed over x squared. And then we have plus g prime of x equals this guy right here, which is 1/3 y cubed over x squared. Great. So now we can cancel this with this as they occur on both sides. Then we have g prime is equal to 0. That means g is equal to a constant, but we don't need the constant in there because we have our standard solution given by f of xy equals a constant. So we can absorb those constants together. So in the end, we've got our solution is described by f of xy equals a constant. In other words, a quarter y to the fourth minus a third y cubed over x equals some constant. And if you want to, you can maybe clear denominators, maybe multiplying by 12 and also x if you want to. That'll give us 3xy to the fourth minus 4y cubed equals a constant times x, where we absorb that 12 into the constant, giving us something that's a little simpler. So that would be our final solution. Okay, so now I'm going to leave you guys with a couple of warm-up exercises. I've got 3 warm-up problems based off what we saw in this video. And so these will all involve multiplying by some sort of integrating factor, being it one of these 3 types or the example that we just did. So the first is 3y cubed dx plus 3y squared dy equals 0. So you can most definitely solve this a different way. This is a separable differential equation, but I think maybe for practice sake, it's best to do it with the integrating factor. The next one is y squared dx plus the quantity xy squared plus 3xy plus 1 over y dy equals 0. And then finally, 12x squared y squared plus 6 plus 6x cubed y plus x over y, y prime equals 0. And that's a good place to stop.